I'm Nadir. I'm a grad student here in physics at UC Berkeley, doing research on cloud physics and its relationship to climate change. So my research involves detailed study of the formation of clouds with an eye towards improving how clouds are represented in climate models, the climate models that people use to predict how much the globe is going to warm in the coming 50 to 100 years. Is pretty well known. There's a lot of variability in these predictions, and so if you ask a climate scientist or you read one of these reports about global warming, well, how much is the Earth going to warm on average in the next say 50 years? You'll find that all that science can say right now is that it'll warm between 2 and 6 degrees Celsius. So that's a huge range, right? And that's Celsius, so that's like roughly 4 to 12 degrees Fahrenheit. If you're at the upper end of that and you're, and the climate warms by an average of 12 degrees, and it's known that the north is going to warm more than the sort of equatorial and tropical regions. So you can anticipate, even more warming up in the north. Well, that's going to give you, increased melting of sea ice, and therefore higher sea levels. So what me and my advisor work on is we've created, my advisor has created a model of the atmosphere. So you take the laws of physics that govern, how the air moves and how water evaporates and condenses and heats up and cools down. When you want to figure out what a very complicated system like that atmosphere is going to do, it's impossible to solve those equations for the whole atmosphere with pencil and paper. And so what you do is you make a model, you create a kind of three-dimensional grid made up of discrete points, and then you can solve the equations that describe the atmosphere just on those discrete points, and you can get a computer to do that. It's the atmosphere is large and it's complicated, and so even when you put it on a computer, you still need a lot of computer power to solve these equations with any kind of accuracy or resolution. And it's only within the last maybe 10 or 20 years that the computers have become powerful enough that we can make reasonably accurate models of the Earth and the atmosphere and run them for 50 or 100 years and have it tell us something reasonable about what we can expect about the climate, about what the temperatures are going to be, what the rainfall is going to be, things like that. The problem is that there's slightly different ways to construct these models, and the different models give pretty different answers. And so much of climate science these days is focused on improving the models so that the different models give answers that are in better agreement. And it turns out that the biggest source of uncertainty in all of these global climate models is the way the clouds are represented. Clouds themselves are extremely complicated, and clouds they're not huge, right, relative to the size of the globe. But there's all this physics in them, water and ice evaporating, condensing. The water and ice that do condense, they might stay up there and float, and that's what we see as clouds, or they might precipitate down, and that's what we see as rain and snow and hail and sleet and all these other forms of precipitation. So they're pretty complicated beasts, and it's very tough to, model them accurately, but then also include them in this huge global climate model. Because the scales at which the global climate model is working, is not the scale at which you can really understand the physics of clouds. So that's a tough problem.